Hey everyone, welcome to this explainer. If you're an industrial professional or a business owner, you already know that membrane cartridge filters are the absolute backbone of your operation. Today, we're going to decode the technical specs of these filters to make sure you're selecting the exact technology you need to protect your specific setup. These filters play a massive role in sterile filtration and bioburden reduction, handling everything from bacteria down to microscopic phage. But making the right choice? Well, that requires navigating a pretty complex matrix of materials, structures, and ratings. So let's dive right in and make that whole process crystal clear.
Let's start things off by cutting right to the chase with a crucial question. Is your current filtration setup silently draining your budget? Because, look, relying on the wrong filter doesn't just mean a minor dip in efficiency. It can lead to massive costs through bioburden contamination, totally reduced flow rates, and unexpected, costly downtime in your continuous operations. Getting this right is really about securing your final guarantee of liquid or gas cleanliness.
To get us there, we've laid out a really clear decision tree for today. We'll quickly hit the basics of membrane filtration, tackle hydrophilic versus hydrophobic options, figure out how to choose the right structure, break down the 5 common materials, and wrap up by optimizing your actual industrial process.
All right, step 1, basics of membrane filtration. Our first stop here is just making sure we're firmly grounded in the baseline technology required for secure microorganism removal.
Before we get into all those advanced polymers, let's make sure we're on the same page about what a membrane is actually doing. Microporous membranes are incredibly thin. We're talking roughly 100 microns here. But despite being essentially paper thin, they're highly porous. And the real magic? Those countless microscopic pore openings are controlled with just a staggering degree of precision. This gives you, the operator, the power to select a barrier tailored for highly specific microfiltration tasks.
And wow, this number really puts that precision into perspective. 0.02. In gas filtration, we can literally filter out microscopic phages and viruses down to 0.02 microns. I mean, that is a truly microscopic defense line, ensuring your sterile environments stay completely uncompromised.
Now, as you build out your liquid filtration system, your target micron rating dictates your exact line of defense. It's basically a sliding scale based on your contaminant. Starting at the bottom, a 0.1 micron rating takes care of Mycoplasma. Step it up to 0.2 and you're catching bacteria and standard microorganisms. Jump to 0.45 for general spoilage organisms and bioburden. And finally, a 0.65 micron rating is your go-to for nabbing spores and the larger spoilage organisms. Your exact contaminant dictates this very first critical choice.
Moving right along to step 2, hydrophilic versus hydrophobic membranes. Once you get your size requirements dialed in, we hit our first major binary choice.
And that choice is assessing the chemical nature of your liquid. Membranes are natively one or the other. Hydrophilic basically means water-liking. These guys easily wet out, making them highly effective for polar liquids, your standard aqueous solutions. On the flip side, hydrophobic literally means water-disliking. You're going to specify these for non-polar liquids, like aggressive solvents and chemicals, because they offer way higher chemical compatibility. If you get this backward, well, your filter just won't wet or function in your process at all. Definitely a headache you want to avoid.
Next up, step 3, choosing the right structure. This branch of our decision tree requires evaluating the physical demand and runtime of your specific operation.
So we have to look at the internal structure of the membrane itself. Think of a symmetrical filter, kind of like a highly precise uniform brick wall. The pores are totally consistent all the way through, giving you an incredibly even filtration across the entire surface area. But an asymmetrical filter, that acts a lot more like a funneling net. It has a varying core size, specifically a reducing gradient. So it catches the big boulders, so to speak, at the top outer surface, and then traps the tiny pebbles deeper down inside the structure.
And why does that gradient matter? Well, because of it, asymmetrical filters give you significantly higher flow rates and a much longer surface life. Honestly, they're the absolute go-to for continuous 24/7 operations or as a pre-filter. On the other hand, symmetrical filters remain the gold standard for absolute precision. That's exactly why you see them everywhere in pharmaceutical manufacturing, fine chemical production, and pure water purification, where absolute consistency is simply non-negotiable.
All right, section 4, the 5 common materials. This is where things get really interesting.
We can actually distill this vastly complex filter market down to just 5 core materials used in process industries today. This is where you align all your previous decisions with the exact polymer. First up, PES. It offers super high flow and low protein binding, so it totally dominates biopharma and food and beverage. Then you've got PTFE, bringing extreme chemical and temperature resistance. perfect for aggressive chemicals and sterile gas. PVDF gives you broad chemical resistance, great for electronics and biologicals. Nylon? It's highly durable, sure, but nowadays it's mostly tied to older, validated legacy processes. And finally, cellulose. It's cost-effective, but mainly relegated to legacy niche water treatment today.
Let's zoom in on performance for a second. Say flow rate is your absolute top priority. Check out this crazy difference. Unlike standard membranes that are just cast, PTFE is produced through a controlled stretching process. This unique manufacturing trick gives PTFE an 80% void volume, which is basically the amount of free space inside the structure. Compare that to just 66% for standard cast membranes. That effectively doubles your flow rate. But the catch is, PTFE is one of the more expensive options, which is exactly why PES remains the crowd favorite for standard liquids.
It's also super critical to see how this tech has evolved over time. Cellulose was literally the first commercial cartridge back in the 50s and 60s, but it struggled with wetting consistency. So, nylon stepped up as the durable industry workhorse through the 70s and 80s. But then, late 1990s, boom, PES hits the market and basically takes over as the predominant liquid filter because of its high flow rates and ease of manufacturing. Knowing this timeline is a great way to figure out if your plant is secretly bottlenecked just because you're using legacy products that have quote-unquote always been there.
And that brings us to our final step, optimizing your industrial process.
Let's turn all this into an actionable playbook for your business. If you treat these 4 steps as a strict operation procedure, you turn highly technical data into a killer specification tool for your production line. Number 1. Target your specific bioburden to set your micron rating. Number 2. Check your fluid's polarity to choose hydrophilic or hydrophobic. Number 3. Evaluate your runtime to pick a symmetrical or asymmetrical structure. And number 4. Match all of that up with the perfect polymer for ultimate chemical compatibility.
So I'm going to leave you with this final thought. Given the massive evolution in filter flow rates, structural void volumes, and chemical resistance over the last couple of decades, isn't it time you audited your own legacy setups? Are old nylon or cellulose filters secretly bottlenecking your continuous operations and costing you serious efficiency? Take a hard look at your process line, because the absolute best filtration options for industrial professionals and business owners are out there just waiting to optimize it. Thanks so much for joining me on this explainer, and hey, here's to cleaner, faster, and way more efficient operations.